presentation of our device.
Thank you, Dan. So my name is Joey. I'm a neuroengineer, and I'm the head for the next-gen team at Neuralink. So for persons with spinal cord injury, the connection between the brain and the body is severed. The brain continues functioning normally, but it's unable to communicate with the outside world. You've already heard about how we can use the N1 link as a communication prosthesis to help someone with spinal cord injury control a computer or a phone, but it can also be used to reanimate the body. Let me show you how. First, a little neuroanatomy. Movement intentions arise in motor cortex and are sent down long nerve fibers through the spinal cord. These are upper motor neurons. In the spinal cord, they synapse, that is, make a connection with another motor neuron, a lower motor neuron, which sends these movement intentions to the muscles, which contract, and in turn, you have movement. While, of course, there are many other circuits involved in voluntary movement, you can think about the spinal cord as many pairs of these two connections. And in spinal cord injury, one of these connections is severed, unable to make the muscles contract. Let's zoom a little bit further. So here you can see on the left a cross-section of the spinal cord with a fiber coming down schematically. This travels through the white matter tracts. This is the upper motor neuron. And then it synapses within this butterfly-shaped region of gray matter in what's known as a motor pool. In the motor pool, the lower motor neuron descends out the ventral roots to the muscles, which contract. And then the sensory consequences of those movements, for example, the touch of your hand against an object, return to the spinal cord through the dorsal roots and ascend the spinal cord up into the sensory regions of the brain. Again, in spinal cord injury, this connection is severed. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. But this is very hard to do. The spinal cord is quite delicate, and it moves significantly within the bony spinal canal. This could cause damage to the electrode, it could cause damage to tissue, or both. But our electrodes are small and flexible, and our robot is able to insert them deep into tissue, perhaps all the way down into the ventral horn of the spinal cord. And so we have done just that. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Now, to track movement, it's very common to use motion capture markers, like you might see in the production of a movie. These can be placed with a light adhesive, and you can see me placing these on my hand. We're going to use these markers to let us zoom in on movement in the next couple of slides. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's do that. So here's a pig, a happy and healthy pig doing what pigs like to do, which is root around for food and snacks. And as you'll see on the floor, there's a blue square. This is a voluntary engagement zone where the pig places itself, indicating that it's comfortable to receive stimulation. When it's in this zone, we stimulate, and if the pig leaves this zone, we'll stop stimulating. And as before, you can see we're able to track the position of the joints and also stream neural data as well. Okay, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. we can stimulate on a great variety of threads and produce different movements and actually sequence them spatial-temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. Okay, so stimulating the spinal cord is only one piece of the story. You also have to get command signals for the stimulation of the spinal cord. Unfortunately, we have a way to do that. We have the N1 link that you've already heard about placed in motor cortex. How would that work? So we place threads in motor cortex and record spikes. These spikes would be wirelessly transmitted in real time and decoded into patterns of stimulation. Stimulation would then be delivered to the ventral horn of the spinal cord, to the appropriate motor pool for the muscles that we'd like to activate. We then stimulate, activate those lower motor neurons, which causes the muscles to contract and movement to occur. Now, of course, movement without sensation is actually kind of difficult. Just think about what it would be like to try to move your limbs if they're numb. But we can also get sensory information as well. So the sensory consequences of your movement can be recorded in the dorsal horn of the spinal cord in the form of spikes. For example, here, a feather touching the hand. These spikes can in turn be decoded in real time, sent to patterns of stimulation to either the same N1 device in the brain or perhaps a different one in a sensory area. Stimulation of that part of the brain would cause percepts of touch and proprioception, closing the loop. So putting those two loops together, we have motor intentions decoded from the brain, used to stimulate the spinal cord, causing movement, and then the sensory consequences of those actions being recorded in the spinal cord to stimulate the brain, causing perception.